Hi everyone. This video is the solution to example 4 of plastic beam analysis, which is going to be the last example that we're going to cover in video. This is a very complicated structure, so it will have a lot of collapse mechanisms. And as you can see, we have the plastic moment, and we need to find the load, which means this will be a capacity problem. Now, in terms of collapse mechanisms, we're going to try to think about which ones we need to consider. The first one, if we think about bar AB, we need to consider one that has a hinge at A, a hinge at B, and then a hinge underneath 3W. And again, we know that this is going to be the critical one because of example 2 that had the exact same shape. So we know we don't have to consider a collapse mechanism that has the hinge underneath the load W. So we don't need to consider this one because we know it's not going to be critical when compared to this one that we just draw. So at least it saves us a little bit of time. Now, the second one we need to consider is at beam BC. So in this particular case, we have a UDL there. So we're going to consider a collapse mechanism that has 3 hinges, one at the left support, one at the right support, and one in the middle. Do not confuse this with the previous case that I said you don't need a hinge here at B, that I said this one you don't need. In this case, you do need, and I'll try to explain why. So in the previous case, the bar CD didn't exist, this little bit. So to make sure this bar can rotate, you don't have to break the bar at C. But in this particular case, because the bar CD exists and it's flat, the only way this goes down is if there's a hinge there, like a knee, that allows for this relative rotation to exist. So hopefully this explains why you need a hinge at C in this particular case, while in the previous one, you don't need a hinge at C. So that's the second collapse mechanism we need to consider. The third one is one that considers the span BD. We're going to think about this case with a hinge at B and then another hinge at the midspan of span BC. So again, this is B, this is C, this is D. And in this case, we don't need at C. That hopefully will make sense when we draw the shape of the collapse mechanism. The final one that we're going to consider is a cantilever failure at span CD. And in this particular case, CD is a cantilever. So you only need a hinge at C to cause the collapse mechanism with this load W. Okay? So plenty of work to be done here. I'm just going to put the loads for us to remember. So we need a W there, and we need here the UDL, 2W. And here we also need the UDL, 2W. But we need this load W. And then the fourth collapse mechanism is just CD breaking on its own as a cantilever. So plenty of work to be done. Let's start calculating collapse mechanism number 1. So we know we only need hinges at the supports and underneath the load 3W. So we can start drawing the shape. So if we assume the rotation to be theta at the left, we know underneath 3W should be 3 theta, and underneath W should be just theta. Now we also know that this rotation here is theta, and we know that on the other side, the angle will need to be 3 theta, so when we multiply by 1, we get the same displacement. Similar to the previous cases, we have all these MPLs applied at where the hinges are, so we should be able to get our equation straight away. So in this case, we're going to get 3W times 3 theta plus W times theta. And this is going to be equal to how many MPs thetas we have. We have 1, then 2, then 3, then 3. So that's 6, that's 8. 8 MP theta. And again, theta simplify. And now we're going to find out that we have 9W plus W is 10W equals 8 MP. So MP is going to be equal to 60. That means now W will be equal to 48 kilonewton. Okay, so we've done one of the collapse mechanisms. Let's go into the second one. The second one is the one with the UDL, and the UDL is equal to 2W. So if we draw our deformed shape of our collapse mechanism, we know all of these angles will be equal to theta, because this is all symmetric. And as we discussed last time, we need the displacement not underneath the center, but underneath the center of each half. So in this particular case, since the entire span BC is 2 meters, that is going to be, half is 1 meter, so this is going to be 0.5 theta, and that's also, let's say, theta over 2 as the displacement. The load will be equal to 2W times 1, so it will be equal to 2W here and 2W there. So now we're at a situation to put 2W times theta over 2, and now we'll multiply this by 2 because we have 2 of them, and this is going to be equal to, and now I forgot to put the MPs, but similar to before, all of them there. So we have 1, 2, 3, 4, so we have 4 MPL theta, and now we can simplify the theta, so we can simplify these 2's as well. So we get that 2W equals to 4 MPL, and knowing that MPL is 60, W is going to be equal to 120 kilonewton. Okay, so we can stop here and start thinking already about which one of these two is critical. So we have 48, we have 120. So we're talking about a capacity problem. So the capacity of this beam is defined by the smallest load that causes the collapse mechanism. So in this case, the 120 will not be critical, and so far the 48 is the critical. So let's move on into the third collapse mechanism. In this case, this is the only one that is multi-span. It's quite an interesting case, this one. So we're going to have a hinge here and a hinge here in the middle. And I'm going to show you why you don't need a hinge at C. Because what's going to happen in this case is when we assume a rotation of theta here, and then we have the hinge there to allow us to close our deformation here at the support, what we're going to see is that the deformation will have the span CD deforming upwards. And there's nothing wrong with that. This is a collapse mechanism that could be the one that causes the collapse of the load. Now, what's the difference between number 2 and number 3? The number 2 and the number 3, the difference is the hinge at C. So if you think about the second one, it has a hinge here at C, while this one doesn't have a hinge at C. And that's why the beam has to continue going upwards at CD. Now, let's look at the deformation here. So if this one is theta, we need to go and check the dimensions. So we know it's 2 meters, and then CD is 1 meter. So if that's theta, we know this bit here is 2 theta. That means this bit here is also theta, and that bit over there is also theta. So all of these angles are also equal to theta, also equal to theta. Now, what we know about the loads is we have a UDL of 2W, and then we have this other load here of W. So now let's have a look. We know we need to break the UDL in 2, so let's put 2W times 1 here, 2W times 1 there. It's a similar case to the previous one, so we need this displacement here is theta over 2, that one is also theta over 2. So now, if this bit here is 1 meter, and we know that angle there is theta, we know that this displacement here at D is actually theta but upwards. And what does that mean? What means is that the work done by the load W, it's actually going to be negative. So the load W is actually helping the structure not breaking according to this mechanism. Let's check the numbers, and then this probably will make more sense. So the first thing we need to do is 2W times theta over 2, and times 2, right, to account for the 2 of them. But now we need to do minus W times theta. And this minus sign, again, what this means is the W and the theta have opposite directions, which means this is actually a stabilizing load. Okay, it's a load that if it didn't exist, the collapse mechanism would be more critical. So that's the way you do it. And now this equals, and now how many MPs we need? We need 1, 2, 3, and not 4. Remember here, we don't have a plastic hinge. So there, we don't need to consider the MP. So how many do we have? 1, 2, and 3. So 3 MPL theta. So what do we get at the end? We get that the thetas simplify. The 2's also simplify. So we get 2W minus W. So we get just W equals 3 MPL, which means W is equal 3 times 60, so that's 180 kilonewtons. Okay, before we move into the next one, just stop and think about what would happen if this W didn't exist. If this load wasn't there, this collapse mechanism wouldn't have this negative term. This wouldn't exist, which means that instead of W, you would have 2W, which means your collapse mechanism would be 90 and not 180, which is less, which means it's more critical. Now let's do the fourth collapse mechanism here, because this is this is a very simple one. And in this case, it's just a bar with a hinge on the left side. So we're going to have a certain rotation theta, which means this displacement here is going to be equal to theta. And remember that this bar is 1 meter long. So underneath the load W, we will have theta. So the equation in this case is nothing more than theta times W, or W times theta, is equal MPL times theta. And in this case, we can see that only one hinge will cause the collapse of this part of the structure. So that's why you only have one MPL theta. So at the end, we can say this is equal to 60 kilonewton. So a very long problem with 4 different collapse mechanisms. But at the end, the critical one was actually found in the beginning with the 48. So the critical one is 48. The critical collapse mechanism is collapse mechanism number 1. And all the other ones will not be critical, which means they won't occur unless we change the loads or we change the dimensions of the structure for this particular one. That's the right answer. We covered a lot of examples here. I hope you enjoyed this video, and keep practicing your collapse mechanisms and your plastic analysis. And thank you for watching the video, and have a nice day.